All right, so remember when we did forces and gravitational forces, we said like, hey, if you are far from the Earth's surface, the force of gravity is not mg. It was given by this force of gravity is g m1 m2 over r squared, right? We talked about that in the last unit. And so the work done by gravity is not mgh, right? The mgh comes from the fact that we assume that the force of gravity is about constant, that force over displacement, right? That work calculation is force displacement. And if the force is mg, then it's mgh. That's literally where that kind of comes from. But if the force is not constant, then it's a little bit more complicated. And I can't derive this for you. This would require some calculus for the derivation, so I'll do it for the Physics C students. But generally, the gravitational potential energy, if you consider this, is given by this formula, where R, there's a couple of things I want to point out to. R is the distance between the center of the two objects, just like the force of gravity. M1, M2 are still the masses of the two objects, and G is still that gravitational constant. So it looks very similar, except it's over R. But I want to point out a couple of things. One, there's a negative sign in here. So you might be like, that seems weird. Is it always a negative amount of gravitational potential energy? And the answer is yes, it is a negative amount, because it has to do with it. Why does it have to do with that? Why is it negative? The reference height, when we do this, there's an assumed reference height, right? And so when we're talking about gravitation when you're far away from the Earth's surface, it actually doesn't make sense, because we might be talking about like gravitational potential energy of a moon and a planet star, and it's like, where is the h equal to 0? And the most convenient place we do this for this model, if we use this gravitational potential energy formula, which is that the reference height is assumed to be infinite distance. Like h equals 0 is way over here at an infinite distance away, okay? Because that's like the only thing. You might be like, well, that's infinite distance. And so like, you're infinite distance away, so anything below it, closer, is going to be negative potential energy. That's why all gravitational potential energy, when you're considering planetary systems and very, very, very far away objects, and you want to consider that, is we assume that the h is not necessarily we get to choose it. It is already assumed to be at infinite distance. And that assumption is how this formula get derived, by the way. Okay, so in this case, you don't get to choose the reference height. The reference height is infinite distance, and anything below it is negative. So that's why it is. Now, I want you to be very, very careful with this formula, because normally, if we talk about things with a denominator, if you have a smaller r, that means they're closer together. Okay, so this is the proportional reasoning part. If you normally have a smaller denominator, that means the number is bigger because you're dividing by a smaller number, right? That would make it bigger. However, this negative sign changes that ordering, because you got to remember that negative 10,000 is smaller than negative 100. Right? So just because it's bigger in magnitude does not make it more energy. Remember, energy is a scalar. And when we think about whether I have more energy or less energy, has to do with if it is more negative, this is less energy. Right? If it's negative 10,000 joules versus negative 100 joules. So when they are closer together, there is less potential energy, which makes sense. When you are closer to the Earth, your potential energy with you in the Earth system is smaller when you are closer to the Earth. You have more potential energy when you are further away from the Earth. Okay, so it's kind of reversed because of the negative sign. So it's one thing to be very careful of when you're doing comparisons of when there's more or less energy, is that if this number is bigger, quote unquote bigger, the magnitude is bigger, it just means it's more negative. More negative is a smaller number. That's how we order numbers, right? Order scalars. So that's one thing to be very, very careful about when you're doing that. Two objects are closer together, potential energy is more negative, which is a smaller amount of energy. So let's go through an example here. We have an average size asteroid located this from the Earth, okay, with a mass of 2 times 10 to the 13, and the distance is 5 times 10 to the 10, right? Drawing those pictures. It's headed towards the Earth with a speed of 2,000 meters per second. What will the speed be just before it hits our atmosphere? Assume the radius of the Earth is 6.37 times 10 to the 6. Let's see. And then the mass of the Earth is 5.97 times 10 to the 24. Okay, so first step is, what is our system here? We're going to include both of them so we can do that gravitational potential energy. It'll be the asteroid plus the Earth. Okay, so then we're going to draw our free body diagrams, and they're going to have forces of gravity acting on each other. But that will be internal to the system, right? Because the system consists of both objects, and they're just pulling on each other. So the work is going to be zero. There are no external forces doing work on it, which implies the change in energy is zero, right? Because work is the change in energy. So we need to think about the energy at this point here. And because we've included the Earth, or we've included both objects, we're going to talk about the kinetic energy of the asteroid, which is 1/2, we'll call it mass of the asteroid, v squared. It has some kinetic energy, plus it has some gravitational potential energy here, which is going to be negative g m1 m2 over r. So let's plug in some numbers here. This is going to be 1/2, 2 times 10 to the 13. V squared is going to be 2,000. Then minus 6.67 times 10 to the 11. Let me move this over so we can have more space to work, so it's not such a complicated formula. Okay, so cool. There's that. Times the mass of the Earth times the mass of the asteroid divided by the distance. Now the R, this number is so much bigger than this, so you don't have to include this part here. I know I didn't draw it to scale because this is 10 to the 10, this is 10 to the 6. This is 10,000 times bigger, so it doesn't really matter. You could do 5 times 10 to the 10 if it was to the surface. You can also add 6.37 times 10 to the 6. If you do the calculation, you'll find that this guy has really no impact. He's going to have a less than a 0.01% impact on the answer, so it doesn't matter if you put it in there or not. So we have a number for the initial energy, 0.5 times 2e13, 2,000 squared minus, just typing it into the calculator, I'm going to get negative 1.6 times 10 to the 39. Okay, you might be like, oh, that seems like a really, really big number. Now, don't use this rounded value. When on your calculator, use unrounded values because it's going to matter. Because now I'm going to talk about the energy right before it hits right here. Now, remember, our H is not 0. So when you do the gravitational potential energy, we're going to have kinetic energy. We're going to have gravitational potential energy. However, when it hits the atmosphere, like, we're not at a distance. The R is the distance between the two objects, which is the radius of the Earth. So don't assume that the R should be 0. R is not the distance to the surface, or the reference height is not at the surface. The reference height is way over far, far, far away. R is the distance between the centers of the two objects. Okay, so this is going to be 1/2 times 2 times 10 to the 13 squared minus 6.67 times 10 to the 11 times 5.97 times 10 to the 24 times 2 times 10 to the 13 divided by the distance, which is now, just because it's very close, it's hitting the surface of the Earth, or like the atmosphere, 6.37 times 10 to the 6. Oh, there's a v squared here. And because that's our expression for the final energy, and because there's no change in energy, this number here is going to equal like that. So this is just a ton of calculations you have to do. So we're going to take this number, we're going to add this guy over. So plus 6.67 E11 times 5.97 E24 times 2 E13 divided by 6.37 E6. Okay, then times 2 divided by 2 E30. You can use Desmos for this. You don't have to necessarily do it the way I'm doing it. And then, oops, this is v squared. And then take the square root of that answer. And I get, let me do the math real quick. Okay, I made a slight mistake. I didn't write the negative 11s here. So this number ended up being negative 1.21 times 10 to the 21. And so this should have been negative 11. But I just want to show you how I put it in Desmos. So in Desmos, I did the initial energy. I did 0.5 times mv squared, like this part here. And then I went ahead and typed in, let me see if I can make this bigger. Typed in this expression for the calculating the gravitational potential energy. And I got this number. Then I'm going to take that number, right? That number there. I called it E0. Oops. So we're going to make this negative 1.21 times 10 to the 21. We're going to add this quantity over here. Then we want to multiply by 2, divide by m, and then take the square root. So I end up getting the velocity here is 1950 meters per second. Okay, so that is the way to use the gravitational potential energy. And if you try to do it with kinematics or forces in kinematics, like you would need to know calculus, because the force is changing. As it gets closer, the force is, of course, increasing, right? And so the force is not constant, which is why we can't just use force times the displacement, because the force is going to vary as he moves closer, right? So it's not a constant force in there. All right, let's look at another example. What's the kinetic energy of a satellite of mass m that orbits the Earth of mass big M in a circular orbit of radius r? So let's think about here. We have a satellite here, mass little m, mass big M, and it's orbiting with the radius r. And we want to know what's the kinetic energy here. And you might think like, well, what does this have to do with the gravitational potential energy part? Well, let's look at. Actually, sorry. What I think this wasn't supposed to be what's the kinetic energy. What is the total energy? Total mechanical energy of a satellite Earth system. Okay, has a mass m. So the goal was to say, can you calculate the total kinetic and gravitational potential energy from here? Well, that means it's going to have 1/2 mv squared and then minus g m big M over r. We know the gravitational potential energy because we know all the quantities there, but we need to know what this part here is. Okay, so let's take a look at that, right? This would be the total energy. So how are we going to figure out that v part? Let's take a look. Well, we're going to draw our free body diagram, right? Centripetal acceleration, so this is going to be force of gravity. And then we have a centripetal acceleration in that direction. So when we do F net equals ma, we're going to have the force of gravity, which is g big M little m over big R squared. And that's centripetal acceleration, so that's going to be v squared over r, right? The r's cancel, the m's cancel. You get v squared is equal to g big M over r, like that, which we can then plug into here. So we get 1/2 little m gm over r. Okay, so we can plug that into there, and then minus g little m big M over r. And look at this. There's a g little m big M over r. There's a 1/2 minus 1. That's going to be negative 1/2 g little m big M over r. Because you can have 1/2 of these minus 1. That's going to be the total energy here. And there's an interesting relationship between the kinetic energy and the gravitational potential energy. When it's orbiting in a circular orbit like that, it's exactly half in magnitude, but obviously signs, right? The kinetic energy ends up being negative 1/2 of the gravitational potential energy. You don't need to memorize this result. I just want you to, it's an interesting observation based on the analysis that we have done from previous, as well as the gravitational potential energy. There's kind of that interesting relationship happening there. All right. Now, what about when you calculate if there's more than two objects and we want the gravitational potential energy for multiple pairs of objects? So let's say I have a planet, a star. What if there's like multiple objects? How does it work like objects A, B, and C? The way it works, and this is something you'll have to do, is every pair of objects creates a gravitational potential energy calculation. So if you wanted the total gravitational potential energy, we would want the potential energy between A and B plus the potential energy between B and C, these two, plus the potential energy between A and C. There would be three pairs here, AB, AC, and BC. Every possible pair, only include it once, right? So you'd have three different pairs, but every unique pair of objects in the system, we're going to want to add up pairs of them like that. Okay, so let's take a look at an example here. So we have three spheres. Masses are initially far away from each other, and then the gravitational potential energy of the three-sphere system is 0, which is our normal. This is our normal default at infinite distance. Like that's where h is equal to 0. That's where our gravitational potential energy is 0. The spheres are brought together until each sphere is a distance r from the other two shown. What is the new gravitational potential energy of the three-sphere system? So let's call this A, B, and C. We're going to do these two. So we're going to have negative gm times 2m divided by r. That's these two objects, because this guy has a mass 2m. Then let's do B and C. That would be minus g2m times m, and the distance between them is r. And then let's do A and C. That's going to be minus gm and then m divided by r there, because these two masses are m and the distance between them. So you see this one here is me doing A and B. This one here is me doing B and C. This one here is me doing A and C. So every possible pair has a potential energy, and we just calculate that up like that. So this is 2 of these. They're all gm squared over r. I have 2, another 2, that's 4, another one that's 5. So this is minus 5 gm squared over r like that. Okay, and that's how you would do it for multiple objects.